Warm regards, Dr. Gan. We are from Group 13 and my name is Crystal. So I'll start off with the background. Our team has decided to predict the price of pre-owned Toyota Corolla by using a data set with the historical price of Toyota Corolla along with the related car attributes. Our dataset includes 38 variables and 1436 observation. The dataset was obtained from Kaggle, and the original source of dataset was from the course of material of data mining in engineering at Northern University. In order to fulfill our objective in computing a model to predict price of car, we have decided to split our data into training set and testing set randomly, with 80% of the observation as training set and the remaining 20% as the testing set. The splitting of data was done randomly by using RStudio. This method can help to prove accuracy of our prediction in the later section. And I'll proceed to the data requirement. So as mentioned above, we are using the data set to predict the price of pre-owned cars. We have a total of 9 independent variables and 1 dependent variable. So for the 9 independent variables, it consists of age of car, the car mileage in kilometers, types of fuel that the car uses, horsepower of the car, whether the car is metallic color or not, car transmission, cylinder volume in the cubic centimeter, which is denoted in cc, number of doors of the car, and also the last one is the weight of the car in kilograms. So the dependent variable would be the price of the Toyota Corolla. So from here, we have plotted 9 scatter plot of model. So scatter plot of model can determine the relationship between the dependent variable and also independent variable. These are all the scatter plot that we have plotted so far. So this is for the age, kilometer, fuel type, horsepower, metallic color, automatic, cc, doors, weight, and etc. And I'll proceed to data analytics. So for multiple linear regression model with K regressor, this is actually the formula. So the parameter beta naught is the intercept of the regression plane, and this beta over here is the regression coefficient. We have for the epsilon, the model error is with the assumption of normally independent distributed with a mean of 0 and an unknown variance. And I'll proceed to the training set data summaries and visualization. For the training set, our total observation is 80%, which is 1150 observation. So from here, we obtain the summary output of multiple linear regression model and also the ANOVA table as well. The ANOVA table will be shown later. So for the multiple linear regression model, this is the equation after computing the multiple linear regression model. So for the ANOVA table itself, it can be shown over here. So in short, for the summary, for the R square will be 0.859. For the adjusted R square, it will be 0.8579. For the mean square error itself, it will be 1819480.516. Yeah, thank you, Ms. Gan. I'll pass it to Xuanying.
Hi, I'm Xuanying. Now I will explain the hypothesis testing of multiple linear regression. There are 2 types of hypothesis testing that generate for the model. The first one is the global test, and the second one is the partial test. The global test is to test the significance regression, and the partial test is to test the individual regression coefficient. Now let's start the global test, which is f-test. The test statistic f-naught computed using R is 771.446, and which is greater than the critical value of x, which is 1.88. Hence, the h-naught is rejected. Now we proceed to the f-test. Proceed to the partial test, which is t-test. By using t-test, we can conclude that the regressor age, km, field type, HP, CC, and weight contribute significantly to the model because their T value is greater than the critical value of T, which is 1.96. This is a process that we determine by using the t-test. Now, we can conclude that now we know the regressor color, automatic, and door do not contribute significantly to the model. And then we remove this regressor from the dataset and perform the multiple linear regression again. And this diagram shows the summary output of multiple linear regression model. The model accounts 85.85% of variance in the car price. And the average error in predicting price using this model is 1,349 euro. And now we have the fitted model of this equation. And this diagram shows the ANOVA tables, and from this table we can see that after removing the regressor, both the R square and adjusted R square is decreased. This is because we now have less information and hence the variance will increase. Thank you.
Hi Ms. Gan, I'm Junwei. So as mentioned from Shen Yun, since we have done the second multiple linear regression, so from this point onward we're only looking at the 6 regressor remaining from the second multiple linear regression. So the regressor will be age, KM, field type, HP, CC, and weight. So I'll be talking about confidence interval and prediction interval. So alright, looking at the confidence interval on the regression coefficient. So what does this table actually trying to interpret is actually, as you can see, the regression coefficient confidence interval is actually either on the negative side or the positive side. So this is actually to signify that the beta head won't have a chance to have equals to 0, and this also concludes that it's actually contributing significantly to our multiple linear model. So now proceed to confidence interval on the mean response and prediction interval. So as you can see, as mentioned previously, we obtain the training set and testing set. So actually, since our multiple linear regression model is based on the training set, and we are actually testing it with the testing set. So this observation is from our testing set. So, and then you can observe over here for the mean response confidence interval is actually 13,391 and 13,618. While for the prediction interval, it's actually very much wider. It's actually from 10,855 to 16,154. So I'll proceed to model adequacy checking. Now, we obtained all of these 5 from the lecture notes, and I will not go into details. So I will just explain what method we use for the model adequacy checking. So we have used summation of residuals, normal probability plot, QQ plot against fitted value, and plot against regressor. So for the sum of residuals, where we have the mean, where we have to prove the mean of error having a 0, this is due to the mean equation of having summation of EI over N. So since the summation of EI is 0, the mean of error is 0. So I will now proceed to normal probability plot, QQ plot. So as mentioned in our report here, if the data is following a normal distribution of mean mu and variance sigma squared, the plot of theoretical quantum versus the standardized residual should be approximately linear. So as you can see in the graph, since this is approximately a straight line, so we will conclude that the fifth assumption, which is the errors are normally distributed, is actually valid. Now I proceed to plot residual against fitted value. So as you can see, we have two plots over here. This is the ordinary plot, or this is the R student residual plot. Actually, this plot actually, I will draw a horizontal band from here first. And since this one has, okay, so actually the horizontal band signifies that the residual won't have a obvious pattern, and this also signifies that we are having actually a constant variance for the error. Constant variance of the error, right? Alright, so the reason why we decide to use R student residual to plot against the fitted value is due to its feature of determining outliers and also sensitive in indicating potential influential point. So I will now proceed to residual plot against the regressor before concluding what is the result from here. So since as you can see over here, we have 6 graphs. So I will just talk about the age, km, and weight. Okay, as you can observe, we actually can plot a horizontal band over here. So, alright. So what fall out of the horizontal band, the 4 and -4 limit, is actually what we think is the potential outlier. So, alright, those are from here, here, and here. Right. Now I can conclude from the plot versus fitted and plot versus regressor that since they have a horizontal band pattern, right, means that our assumption on the linear relationship on the response and regressor is true, at least approximate. So, and then we also proceed to conclude that our error term is having a constant variance sigma squared. Now this is all from my part, and I will pass the stage to Xingwei. Thank you.
Hi Ms. Gan, I'm Xingwei. And just now Junwei already mentioned about the outliers. Now that we know all these outliers, we want to know how does these outliers affect our model. Therefore, we will try to find the leverage points and the influential points. Leverage points are points with unusual x value, and influential points are points with unusual x and y value. We will assume observations with HII bigger than 2 pm to be leverage points. Using RStudio, we found out that all these observations are leverage points. However, not all leverage points are influential points. There are cases where leverage points with large head diagonals have almost no effect on the regression coefficient because they lie almost on the line passing through the remaining observation. Okay, now if you look at the table, we can see that 179 and 775 have extremely large head diagonal. This could be an indication that they might be influential point. Now, influential point are points with a noticeable impact on the model coefficients in that it pulls the regression model in its direction. Under the Cook-Stee method, we found out that 179 and 775 both have Cook distance larger than 1, hence we will assume that they are the influential points. Under the DFF-ITS method, the cutoff point is 2 square root Pn, so any observation with absolute value of DFF-ITS larger than 2 square root Pn is considered to be an influential point. Using RStudio, we found out that all these observations are influential points under the DFF-ITS method. However, DFF-ITS method is a more sensitive approach as it detects more influential points, but sometimes it identifies more data points than the analyst might wish to analyze. Therefore, adopting a diagnostic view, we realized that 179 and 775 have extremely high absolute value of DFFITS, and the rest of the observation, DFFITS is actually really close to the cutoff value. So we will only assume these two observations to be influential. Now that we know these 2 points are influential, we want to know whether we should discard them. Not all bad influential points are not all influential points are bad values. Sometimes they might be valid and there is no justification to remove them. Therefore, we will move on to the next session where we remove these 2 influential points and perform multilinear regression again. And we realize that when we remove them, there's extremely obvious reduction in the estimates of beta 3, beta 5, and beta 6, and the intercept changed drastically with a negative 500%, nearly 500%. MS-RES and adjusted R-square would be improved as well. So we went and looked at the values of the regressors of these 2 points and found out that both of them have extremely high weights. Most of our observations had weights ranging from 1000 to 1200 only. However, these 2 had weights ranging from 1006 to 1480, which is nearly 1500. And we found out that 1600 to 1500 cars are usually a compact truck or an SUV, but Toyota Corolla is a compact car only. Therefore, we assume that there might have been an error in measuring, or the observations were not part of the population that was intended to be sampled. So we concluded that it would be appropriate to discard them to improve the accuracy of our regression model. Thank you. That is it.
Hi Ms. Gan, I'm Yong. Now I'm going to talk about the multicollinearity. Multicollinearity exists when there is a linear relationship or correlation between the regressor. To predict which regressor has a higher correlation with other regressor, we have several techniques, which is the correlation matrix and the VRF method. From the correlation matrix, we can see that in between 0.7 and 1, there's a strong level of correlation. So in this table, we can see that the field type we have a strong correlation of 0.7 with CC. And the field type has a moderate correlation with HP and weight as well. This indicates that the field type might have a multicollinearity issue. Hence, we will use VRF in the next section to analyze further. So when we perform VRF model in the R program, we can see that the field type is 5.7, which is higher correlation with the other regressor. So after we remove the field type, we can see our model is slightly decreased in the R square and the adjusted R square, but slightly increased a bit in the MSE. So this is because we now have less information and hence the variance will increase. Now I'm going to talk about the accuracy testing for the fitted model. To test our fitted model whether it's accurate or not, we are using the external data, which is the testing sets. So when we're using the testing set for our fitted model, we found that the MSE for testing set is 1.5 million and the training set, which is 1.8 million. So we found that our MSE test is smaller than MSE trend. This signifies that the residuals between observed value and fitted value that we obtain by inserting values from the test dataset is nearer to each other compared to training set data. So we can say that our fitted model is good enough to predict the external data. So in conclusion, this is our summary table for our whole experiment. There's 2 advantages for the multiple linear regression. After performing F-test, T-test, and multicollinearity test, we found that H, KM, HP, CC, weight is the regressor that we need to fit for our fitted model. So the second advantage is ability to identify the outliers. In our dataset, we obtain many outliers. However, The only observation 179 and 775 have strong influence over our model. We analyze this observation and conclude that it is appropriate to discard it due to its extreme weight. So there's only one disadvantage from our opinion is limited to linear relationship. So when our dataset contain of group categorical data and discrete data, we might not perform well. So the only way we can overcome it is using the generalized linear model, which can suitable to fit for it. So that's our presentation. Thank you for having your time.